Okay, so back to ProVerif. So I just wanted to show you the kind of analysis you can do with the tool on a real-world protocol, and notably TLS 1.3. So TLS 1.3, you've already heard a little bit about it from Mark, I guess, and you may hear a little bit more about it from Kenny, I don't know. But it's the next version of TLS, and it was completely redesigned from TLS 1.2. That's kind of what you need to know, and it's almost done, right? So I think the word we're using is nearly, I think, but or whatever that means. And the big thing that happened for the design of TLS was that in TLS 1.3, they wanted to improve the security, and one way they wanted to do that was to remove all the legacy constructions that we already have discussed were broken. So they just wanted to remove all of the legacy constructions, but at the same time they wanted to make the handshake faster by introducing the zero RTT mode and reducing the latency that is required in the TLS handshake. So these are vaguely contradictory goals, but the idea was to bring them together and to involve the community in verifying this new protocol. So obviously you need extensive security analysis, and that's what a lot of people, even that you will see in this school, have worked on, including Hugo and Mark and me and so on. But one thing that you have to remember is that for the foreseeable future, TLS 1.3 is going to be deployed in parallel with TLS 1.2, right? Maybe even TLS 1.1, 1.0. These guys are not going away anytime soon. And this brings up a new question, which is that, okay, we have designed this completely new protocol called TLS 1.3. We have lots and lots of security proofs about it. Can we be sure that an attacker cannot downgrade us from TLS 1.3 back to TLS 1.2 and then deploy all the bad attacks that we had before, right? That's one thing that we have to be particularly careful of, because after having made so much effort to secure TLS 1.3, we don't want it to be the case that people can always just roll back to some older version which was broken. So how can we verify that TLS 1.3 is secure against such attacks? So what we did was to model this in ProVerif, the whole of the TLS protocol. And when we do that, we can't just verify it against a strong model of crypto. We also want to introduce some weak notions of crypto that will apply when you're using an old version of the protocol, right? So for every crypto primitive, we have both strong versions. We model both strong versions and weak versions. So if you give me the strong algorithm, the primitive will behave ideally in the way that I always say, it's like a perfect cryptographic box. But if you give me the weak version, we'll assume that the primitive is completely hosed, completely broken. So here's an example. So which is for Diffie-Hellman. This is our model for Diffie-Hellman in analyzing TLS 1.3. We assume that there are good groups and bad groups, and even within good groups, there are bad elements and good elements. By a bad element, I mean something which is in the small subgroup of size 0 or 1 or whatever. And by a bad group, I mean a group which is sort of vulnerable to logjam, say. Okay? So in TLS 1.3, I'm guaranteed we will never negotiate bad groups. And let me assume that people are always going to check the received public key so that there will never be bad elements. Okay, so we will never have bad groups and bad elements. But in old versions of TLS, it's very likely that there are bad groups. We know from logjam. And it's also possible that people are not verifying or validating the public keys they receive. So there might well be bad elements involved in the Diffie-Hellman exponentiation. So here's a model that captures both of these notions. So we define a function called DH ideal, which is the ideal notion of Diffie-Hellman, which satisfies this equation, that if you give me a DH ideal, if you do g to the x y, you get g to the yx. Now that's the equation that you get. So there is a function called Diffie-Hellman ideal, and it satisfies that equation. Okay, so this is your classic Diffie-Hellman assumption coded in ProVerif. But our full Diffie-Hellman exponentiation function is actually dhexp, which is our concrete Diffie-Hellman exponentiation. And for this, we have the following rules. First, we say that there are 3 rules for Diffie-Hellman exponentiation. If you give me a weak Diffie-Hellman group, then no matter what exponentiation you're doing, you're always going to get out of it a bad element. Okay, so because if you're a weak group, let's assume that all exponentiations in the weak group go to the number 1. It's a trivial modeling of something that will be forced into a small subgroup, but let's just say everything goes to 1, which is the bad element in if you give me a bad group. Similarly, even if you're using a strong Diffie-Hellman group, but you give me a bad element, such as the number 0 as your public key, if I do your public key to the power my private key, I'm going to get a bad element. So if I do a Diffie-Hellman exponentiation with a bad element, I get back a bad element. Finally, the bottom case is a good case. If you're giving me a strong Diffie-Hellman key, and we are using a strong Diffie-Hellman group, and you're giving me a good element, then Diffie-Hellman exponentiation behaves as expected. So in most cases, we want to be in the third case. Right? In most protocols, we want to be in the third case. But we are allowing the fact that the attacker can try to fool you into accepting a bad Diffie-Hellman group, and even within a strong Diffie-Hellman group, might be trying to fool you into accepting accepting bad elements in that group. So this is a much finer, let's say, model, even though it's still symbolic. It's a final model of potentially compromised Diffie-Hellman that we can encode in ProVerif. And we have a similar model for hash functions with collisions, for RSA encryption, for authenticated encryption, which could be good or bad, and so on. So this is our way of modeling all the kinds of attacks that might come up if you are allowing or supporting weak crypto algorithms. So once you add a crypto library of that kind, you enhance your crypto library to use primitives of that kind, you have to accept that what you have is a model which is overly conservative, right? We are basically saying that the moment somebody uses a bad Diffie-Hellman group, everything is completely broken in that group. Similarly, if somebody gives you a invalid public key, you immediately say that all bets are off. Okay, so it's a bit more conservative than is perhaps necessary. But what we are trying to make sure is to try to get a very kind of strong guarantee for TLS13, even if legacy crypto behaves in a disastrous way. And in a way, we want to future-proof TLS13, so that tomorrow, if a new algorithm then turns out to be completely hosed, we can still analyze whether or not TLS13 will be affected by this. Okay, so once you have modeled a crypto, we can take the nice TLS13 protocol, which you don't care about, and write a full ProVerif model like I showed you for Denning-Sacco. We can write a full ProVerif model for TLS13 clients and TLS13 servers. So we modeled it. It's basically 12 messages in 3 flights, 16 derived keys, and then data exchange. So it looks complicated, but it's actually not as complicated as it looks. We modeled the Diffie-Hellman based key exchange plus pre-shared keys plus 0 RTT. And we also modeled TLS 1.2. And this is an important aspect of this work, which is that when we are trying to prove things about TLS 1.3 or TLS 1.2, when you're trying to prove these things by hand, it's already too complicated to deal with one mode of TLS. Okay, then 3 modes of TLS 1.3. Now, if I asked you to prove something about the composition of TLS 1.3 and TLS 1.2, I'm asking you to import into this the whole model of TLS 1.2 that you might have. That's way too complicated to do hand proofs of. But here, I'm able to just add a model of TLS 1.2 to the model of TLS 1.3, run them both on the same servers and the same clients, and ask whether you can use attacks on TLS 1.2 to break TLS 1.3 connections. Okay? So the whole agile crypto model, which is basically all our weak assumptions, is about 400 lines, and the TLS models for both the protocols comes to about 500 lines of ProVerif. So it's not so much, because we are really doing this at a high level, right? This is just a protocol model. And then we're going to start verifying it. Okay? So to verify it, we've got to decide what our security goals are. So for TLS, we use the following security goals. We're going to prove that all the messages between honest clients and honest servers are secret. They cannot be known to the adversary. We're going to try to prove authentication for messages which are sent from authenticated peers. So, the client gets to know that a message was sent by the server that it thinks it was sent from. We want replay prevention. Obviously, this will not work for 0 RTT, which is vulnerable to replays, as we saw 2 days ago. But you want to check for replay prevention. And you want to prove forward secrecy. So you want to show that if after a handshake is over, if the long-term keys are compromised, you cannot come back and recover the handshake keys. So let's just concentrate on the simplest one, the first one, the secrecy query. So what you want to prove is that messages sent from a client to an honest server are secret. So we mark such messages as message with this constructor. A message con S is a message which is sent on a connection with an identifier con to the server S. And we want to ask ProVerif, can you prove to me that the attacker does not know any message of this form, which is a message which is sent from on this connection to the server S. So all these messages are secret, but for every server we produce a different message, and every connection we produce a different message. And we want to ask that all of these messages are actually kept secret. So if you try to prove that, obviously ProVerif is going to say that query is not true, because what is S? S could be the attacker, right? So messages sent to the attacker are definitely not secret. Only messages sent to honest servers are secret. Okay? So if but what precisely ProVerif will say is that S's private key could be known to the attacker. If S's private key is known to the attacker, then all bets are off. So then you can refine the security goal query, and you can say, oh, okay, can you prove to me that if the attacker manages to obtain the message which is being sent to S, it must be the case that the server's key was either weak or compromised. And the weak or compromised means that if it's an RSA key, then it had better be a strong long-term key, and compromised means that the attacker has actually been able to obtain it. So in either case, we are asking ProVerif to show that the only condition under which the message could be known to the attacker is if the server's key has been compromised. This again, of course, is not true, because in our model, the algorithms that we are using for protecting these messages could themselves be weak. So then ProVerif is going to say, no, it's also possible that the authenticated encryption algorithm you used to protect this message was weak. So so you have to discount the fact that that particular algorithm was weak. So you keep refining your query until we finally find the strongest query that you can prove. And in the context of TLS13, it basically comes down to something like this, TLS13 and TLS12 together, which means that the attacker can know the message, but only under these 5 conditions. Okay? Either the server's key was compromised, or the algorithm you used was the AE algorithm was weak, or the Diffie-Hellman group was weak, or the server used weak RSA decryption with the same private key. By weak RSA decryption, we mean something that is vulnerable to, say, Blankenbacher, or the server uses a weak hash function. And if you say that these are the only cases, then ProVerif will say, yes, that is true. Okay? So now you can go through these algorithms, and you can say in TLS13, what are the conditions that could hold? Do we have any weak AE algorithms? He says no. Okay. Do we have any weak DH groups? No. Is the server that is using TLS13 also going to support RSA decryption with the same key? Unfortunately, yes. So this we can't really discount. So this is a potential attack on TLS13 from a TLS12 attack. Is the server that is supporting TLS13 going to use the same signing key with a weak hash algorithm like MD5? We don't know, because we don't know what it's going to do in TLS12. So if we can guarantee that the TLS12 configuration at the server disables RSA decryption, or at least protects against Blankenbacher in some strong way, and disables MD5 signatures, then we can go through that list and say, okay, TLS13 is downgrade secure. But that's a statement that actually gives you all the preconditions you need to prove downgrade security. So in particular, what we can prove symbolically is that messages on a TLS13 connection are secret as long as the following 4 conditions hold. The connection should not use weak AE, should not use a weak DH. And these 2 are interesting because it's not about the connection. It says that on no other connection in the world should the server support weak RSA decryption, and on no other connection in the world should the server use a weak hash function. And now that's interesting, because this is basically saying that an attack on the hash function on a different session could actually break the security of my TLS13 session. Similarly, an attack on RSA decryption on a completely different session might be able to break my security for my TLS13, even though I'm not using RSA decryption in TLS13. And this corresponds to the nice Blankenbacher attack, which was shown last year. It was discussed in the context of the drone attack as well, where if you have a Blankenbacher attack on TLS12, the attacker can use the Blankenbacher attack as a signing oracle to obtain a signature for a TLS13 session and use it to sign and therefore impersonate the server in TLS13. as long as the TLS13 and TLS12 are using the same signing key, right? And this is, of course, going to be the case because the people are not getting completely new certificates for TLS13. And even if they did, browsers are not going to differentiate between certificates that were issued for TLS12 and TLS13. If they did, then some of these problems would go away. Okay, so this gives you a set of preconditions for downgrade resilience in TLS13, and it identifies the weak algorithms in TLS12 that can affect TLS13 security. So this is the kind of analysis I think we can do with automated tools like ProVerif for fairly large models. This is TLS12 plus TLS13 with a whole bunch of weak algorithms thrown in, and find all these corner cases that we may not have thought about.
If I understand you correctly, you're proving with your secrecy is secrecy of the messages exchanged in the TLS channel.
Mm-hmm.
Is there an intermediate step in your proof where you will have like secrecy of the keys and kind of like as a modular part, but then going to secrecy of the channel?
So ProVerif is kind of a whole program analysis. So we do these kind of intermediate, try to prove intermediate proofs for the session keys. But it doesn't really help us when trying to prove the properties for messages, if that's the question. We have to redo the ProVerif has to redo the entire analysis anyway when trying to prove things about the messages. And since properties about messages are easier to explain to people than properties about intermediate keys, well, not to this crowd maybe, but in general to humans, so we kind of stated in terms of the messages on the channel. But the key properties are, well, if you talk about the session key, then the AE doesn't apply anymore because you're not used AE just yet. But I think these ones still would.
You would get secrecy properties on the keys if you like ask for that.
Yeah, if you ask for the exact query that you ask for. All right. Yeah, sorry. Could you repeat that? I can't hear. So partially, you mean like some number of bits of the secret? Yeah. So in ProVerif, normally we prove one of two kinds of secrecy properties. One is which is called syntactic secrecy, is the kind of thing I've been talking about, where the whole secret has to be revealed or not. There is also a notion of strong secrecy, is what they call it, where you are talking about the equivalence of two ProVerif processes, where in one case, well, it's kind of like real or random, let's say. So there are two values, and you can't distinguish between them. So that is, and those properties, strong secrecy, you can state and you can prove in ProVerif, but ProVerif fails much more on those queries than it does on these ones. These ones it almost always is good at proving. Equivalence-based properties or indistinguishability-like properties, it's harder at proving. But there's nothing in between. So it can either prove that you don't leak any bits or you leak all the bits, but it does not really allow you to kind of go between those two. Okay, so conclusion on the ProVerif side of things. I wanted to show you how these symbolic tools that you may not be aware of, how they can find problems early in your protocol. ProVerif has been used for many protocols like TLS, SSH, Signal, and so on. And it can you can code your own crypto primitives. And like we showed with our weak DH primitive, you can really try to be very flexible about what assumptions you want to use and not. You have to code it in a maybe slightly unintuitive way for you, but it's kind of it's fairly straightforward to add new weaknesses or new assumptions and test your protocol against them. You can automatically find attacks, like the counterexample we saw earlier. But of course, the limitation is we are only looking for attacks of a symbolic nature. These are not the whole range of cryptographic attacks. In certain ways, there are too many attacks that you might find. In certain ways, too few. So the absence of attack in particular does not mean that you have a crypto proof. So the next part that I'm going to start right now is on how to do crypto proofs for models like the one that we wrote right there for TLS and for Denning-Sacco. You take the same kind of model, we've done the effort, we have run ProVerif, we've fixed all the bugs. Now we want to do a genuine crypto proof. Can we use automated tools to do that?
Question. If you had using primitives that were like UC secure, proven as ideal functionalities, and you're entire protocol had no assumption, nothing cryptographic beyond these ideal functionalities. Would a proof in ProVerif then, would a symbolic proof then indeed imply computational proof, or it's not known?
So there are several results called computational soundness results, and they look similar to UC-like assumptions that you have to make on the way you're using the crypto. But they also have to make other restrictions on how the protocol execution works. Primarily because here we have non-determinism built into the systems, and you have to make sure that your version of your analysis of the protocol does not rely on non-determinism in a way that cannot be compiled to a simulator in the crypto proof. Okay, because a simulator cannot use non-determinism, he can only use random coins, but your proof here might be relying on the attacker explicitly doing non-deterministic things, and you have to be sure that you're not relying on those. So there are some disciplines that you can use in writing your model, including the fact that you're only using nice little packages which are nice and modular and composable, and the fact that you're not relying accidentally on some on extra capabilities of the attacker which will not be available in the computational cryptographic model, and then the proofs go through. Yeah, but so far it has never been successfully applied to a seriously large protocol or middle-sized protocol, because there's always too many differences between what the symbolic modeling style is and how the crypto proof works. All right. Sorry, somehow it went back to the beginning. All right, so now we are switching to a second tool called CryptoVerif, also designed by Bruno Blanchet, with some early help from David Poinchevald on designing and figuring out how to do this tool. And the idea here was that we know how to analyze these protocols written in this nice process syntax in the symbolic model. Can we actually do crypto proofs on the same kinds of things? So there's some reading material. I'll encourage you to look at it. So just to kind of clarify again, we've been talking about actually two different models, and now we're going to be talking about the real cryptographic model, which just to distinguish between the symbolic model and the cryptographic model, we sometimes call this a computational model, where all the messages will now be bit strings, and all the primitives will be functions from bit string to bit strings. The adversary will be a probabilistic polynomial time Turing machine. So classic stuff, which you guys fully understand. Traditionally, the proofs in this mode, like we've seen in this school, are done manually, and it takes some effort to check. Let's say that they're correct. Whereas the symbolic analyses I showed you, the primitives are ideal black boxes, so somewhat unrealistically simplified or approximated. Messages are just terms built using an algebra, and the adversary can only use those primitives, has no ability to guess secrets and stuff like that. So they are good for finding logical flaws in protocols, but does not provide a crypto proof. So now the goal is, can we use the same kind of models but actually prove things in this model, which is where we want our crypto proof to be, right? So CryptoVerif is a prover that will allow us to do this, and we're going to see how this works. It can prove secrecy and authentication properties. It has a way by which you can plug in various kinds of assumptions. So if you want to write some weird new Diffie-Hellman assumption, you should be able to code it up in CryptoVerif. And then you can write your protocols like we wrote in ProVerif, the exact same style, in a very similar syntax. And then you can try to prove that the protocol works, satisfies its security goals with an active adversary as from some number of sessions, say n, which is parametric in the security parameter. And CryptoVerif, what it will do is it will produce for you a sequence of games by which you can go from your initial protocol all the way to a protocol which is trivially and obviously correct, and it will give you a concrete kind of security bound by calculating what is the probability of attacker advantage which has been lost or gained in this by the sequence of transformations. And the proof technique is something that many of you will be familiar with. It's using game hopping in the style of Shoup and Bellaret-Ogové. The proof is essentially a sequence of games. The initial game is your protocol, which you're going to specify, much like in ProVerif, using processes. And you go from one game to the other by either applying some sort of syntactic transformation, which does not lose any attacker advantage. It's a purely syntactical transformation, or by applying a cryptographic primitive, which might actually change the attacker's advantage a little bit, but hopefully negligibly. Okay? And the last game after applying the sequence of games is hopefully ideal, which means that the attacker has a 0 advantage for winning the last game. So then by kind of composing all of these transformations, you can prove that the attacker had a small advantage of winning the first game, and you can actually calculate exactly how much advantage he had. So the input is going to be a specification of the protocol in a syntax very similar to that of ProVerif. Then you're going to write security assumptions for the various primitives you're using, and this is not going to be like ProVerif at all. This is a place where we're going to really try to model exactly the kind of assumption that we want, like UFCMA, int CPA, whatever. And you have to provide the security properties, and that will be again like secrecy of something that you want to prove secret. Then you run CryptoVerif, and sometimes you have to help CryptoVerif a little bit. Okay, so it's not like fully automated like ProVerif. But at the end of it, CryptoVerif will output for you the sequence of games and an explanation of how it went from game n to game n+1. So it'll actually give you an explanation of what those game hops are. You can even print it out in LaTeX and put it as an appendix in your paper if you like. It's actually a huge number of games, so you may not want to do that. But and then it gives you an upper bound on the probability of the success of an attack. Okay, and it's a big fat formula, but it then proves also that this formula is negligible in the security parameter. The syntax is going to be very similar to ProVerif. We'll see that in the next slide, but the semantics is different. Yeah.
So typically I get a very huge number of games and a huge number of steps. I wouldn't want to print it out. But if I had already prepared a series of games, I just want to verify that each hop is indeed negligible, whatever. Could I use it to verify that my game-based proof is actually correct?
Right.
Generating it?
You can. So what you would do is if you already have a paper proof and you know that the main steps in the paper proof are these 5 steps, you can tell the CryptoVerif tool, please use the following proof script, simplify the game, apply game 1, simplify it, apply game 2, and so on. And you can just ask it to check that these games are applicable in that order, calculate the actual probability expression, verify that's negligible, and maybe just print out the ones just before and after the games that you care about. And then it will give you exactly the 10 games that you care about, and that might be worthy of including in a paper. So the difference from ProVerif, just to kind of clarify, the semantics is going to be probabilistic, not the process-based non-deterministic syntax that I showed you before. The processes are all required to run in polynomial time. The number of copies we make, earlier we would just write an exclamation mark to say any number of copies. We can't do that anymore. We have to say they can only make n copies. You have to say what the n is for each number of copies, typically, and they have to be polynomial in the security parameter as well. The length of the messages on all the channels that you're sending are also going to be bounded, because if they're unbounded, then again we are in trouble. So it's going to be bounded by polynomials again. And it's sort of inspired by existing prior calculi, which were exactly meant for doing these kinds of proofs. Okay. So let's look at an example. It's always good to look at examples. This is the simplest script I can do in CryptoVerif with some interesting properties. It's encrypt then MAC. Okay, it's a very simple construction. I know it's not a key exchange, but it would take too long to explain key exchange proofs here. In CryptoVerif, it gets pretty ugly. Let's do just simple encrypt then MAC for a message. So A wants to send to B a key, K prime. What it's going to do is and they already share from before an encryption key K and a macking key MK. It just wants to send a new secret value, K prime. So what it's going to do is take K prime, encrypt it under K, then MAC the ciphertext under MK, and send it over. So it's encrypt, then MAC. Yeah? And the goal of this protocol is very simple. We want the K prime, which we are sending, to be kept secret. Okay? Okay, we can also ask for some authentication and so on. Let's just focus on secrecy. So how do I model this in CryptoVerif? So I can write the processes for A and B and the setup processes, much like in ProVerif, but now I will be a little bit more careful on how I'm generating keys and so on. So this is the setup process, Q0. So what it does is generates a new key seed, which are like coins that you generate for key generation, and then calls kgen, which is going to create an encryption key, K. Then it creates a new key seed R prime and use that to create call mkgen, which is going to create for you a new macking key mk. Okay? And then it's going to run the process QA and QB. It doesn't give the attacker any secrets because these are supposed to be secret keys. So it's going to run QA and QB in parallel. Okay? The slight difference between CryptoVerif and ProVerif syntax is that in CryptoVerif you have to keep giving back control to the adversary while you're running your process, because earlier we had non-determinism, so we could use interleaving and non-determinism to allow the attacker to interfere with the protocol whenever he wants. And now we have to be a little bit more careful about making sure that the attacker keeps getting control. So the CryptoVerif has a syntactic rules which force you to keep giving back and forth control between the adversary and the protocol, so the adversary can actually act as a scheduler for the protocol as well. But for now, let's ignore this fact. Let's just think it's looking just like ProVerif. We've already seen one syntax. We don't want to introduce new syntax. Let's just stay with that. All right, so how's the code for A? It's basically what A is going to do is first of all, let's say that A is, okay, let's ignore the exclamation mark. Let's go there. It's going to generate a fresh K prime, calling new K prime, which is a key. It's going to generate fresh nonce R double prime, which is going to be used in the encryption, because encryption now in the CryptoVerif model will take a random input, so that we can actually have we don't want to have deterministic encryption here. Then what it's going to do is to compute this thing called E, which is going to be the encryption of K prime under K using the coins and R double prime. So using that random nonce. So encryption takes a nonce, a key, and a plain text, and it produces for us a ciphertext E. And then we're going to send out on the public channel the encrypted value and a MAC of the encrypted value under the macking key MK. Okay, so this is the process for QA. We are allowing you to have n sessions of QA, and that's how we write this exclamation mark n or exclamation mark I less than equal to n, means that there are some number of sessions or some number of copies of A, which is polynomial in the security parameter. It's not an arbitrary number of copies, but it's up to n copies. And each of those copies of this process is indexed by I. Okay, and this is kind of important. What this means is that if I unroll this right now and I make n copies of QA, how am I going to refer to session number 1 or session number 2 or session number 3? I'm going to use this variable I to refer to that. So each of the variables in this process, including K prime, R double prime, E, and so on, are implicitly indexed by I. This is the ith copy of E, that's the ith copy of K prime, that's the ith copy of R double prime, and so on. Okay? And this is important so that we can actually refer to that particular instance of K, because we have many copies of these processes which are going to be analyzed together. Yeah?
I'm interrupting too much, tell me. So you're fixing n ahead of time here.
Mm-hmm.
This is like if you were doing a cryptographic proof, you're reversing the order of quantifiers. You're essentially saying that you're only proving security against adversaries that have a fixed a priori bound in number of decryption queries they can make.
Mm-hmm. So what we are doing here is n is actually a variable. Okay, it's not a constant. So it's a variable, and the final formula I get out for the attacker's probability of success will include that variable. Okay, so we can actually say if you give the attacker n decryption queries and m encryption queries and c signature queries and whatever, then the probability of success is some formula that includes all of these. And then you can basically plug in different values for these and see what the security comes out.
Okay, you're asking that n is polynomial security parameter, but what's that polynomial? You can say any polynomial, but any polynomial is not well defined.
Right. So for now, we don't care what the n is. We will just compute a formula, and then when you're trying to prove that that formula is negligible, that's when you have to basically kind of nail it down as to say, okay, now how big is n? It's and so on. So, yeah.
Did you say what the goal is of this encrypted mark?
Yeah. So for now, we just want to try to prove that K prime is kept secret. Okay. Okay. We're not using the MAC for that, but for now, we just try to prove that K prime is kept secret. We can also add goals like K prime. Well, they get some integrity for K prime at the recipient, but
If the
Right. That's right. So I'll show you the proof that we have here, and you'll see that that proof would not work for Mac then encrypt. It does not mean that there might not be a different way of or different set of assumptions under which you could prove Mac then encrypt. In fact, there are probably. But for the assumptions we will use, which is int CPA for the encryption and UFCMA for the Mac, you would not be able to prove Mac then encrypt under those assumptions in this model at least. Okay, so just to kind of complete the model, QB, what is it going to do? It's going to receive on the channel some encrypted bit string and a MAC. It's going to first verify the MAC. It's going to verify the MAC using the macking key that it received. And if the verification succeeds, it's going to decrypt the ciphertext, convert the ciphertext back to a key, and then it's going to stop. Okay, so that's the process for B. Okay. So crucially, B computes this variable called k double prime, and that's what B thinks is the key that it received. And A was computing the key called k prime, which is the key that it generated and sent. And informally, k prime and k double prime should be the same, okay? Because k prime was sent from here, and k double prime was the one that the other guy received. And for now, we're not really considering compromise. So QA and QB are both honest. The only thing we have here is really a network adversary. Okay? So it's kind of a fairly simplistic model. So this is your full model for this Mac and encrypt. Mac and encrypt between 1A and 1B fixed. They already shared macking key, already shared an encryption key. All right. So before we start proving the secrecy of K prime, we need to say what the assumptions are. So the most frequently or the most commonly used assumptions for many of these crypto proofs are already there in the CryptoVerif sort of default library. So you don't really have to redefine them. You can just say, I want to use UFCMA, and for these three set of functions, Mac, verify, and kgen, and to just apply the UFCMA assumption for those. But you can also define your own, or you can extend it, or you can modify these assumptions if you need to. And you will, what you will use for the Mac is UFCMA, which is essentially that an adversary who's given access to the Mac and verification oracles has a negligible probability of forging a MAC on a message for which the MAC oracle was not called. Right? This is something that you guys have seen before, just kind of repeating it. The encryption, we are going to use in CPA, which means that an adversary has a negligible probability of distinguishing the encryption of two messages of the same length. In particular, we're going to sort of use a variant of it where we're going to say, if you encrypt the message, or you encrypt zeros of the same length, the adversary can't tell the difference between these two. An adversary who's access only to the encryption oracle, not to the decryption oracle. Yeah? And we're going to assume that all keys in this setting have the same lengths. We don't want to deal with lengths right here, so let's assume that everything is of the same length, so we don't have to worry about length distinguishing. But we actually have to add that explicitly in CryptoVerif, or else it will say, the attacker can tell that the lengths of these two things are different. The security properties you can prove in CryptoVerif, there's two notions of secrecy. Really, you want the second one, almost always. Occasionally, you might be satisfied with the first one, but usually the first one is no good. But okay. What we call one session secrecy means that the attacker is given one test query. So, and using that, he has to break the secrecy of one of the secrets in the protocol. So if you have n sessions between A and B, you are asking that each of the sessions has a key which is individually indistinguishable from random. Okay. And the general secrecy, what you call secrecy, basically says that if you take the set of all keys that were generated by Alice or received by Bob, in this case we're talking about k double prime. You can also ask the same question about k prime, which Alice generated, or k double prime that Bob received. If we take the set of all keys, then this set of keys is indistinguishable from a set of random keys. Okay, so the attacker gets to make many queries and try to distinguish between them. So for example, if you use the same secret key in all your sessions, they are not secret in this sense, but they are secret in the one session sense. All right, so let's see how the model, the UFCMA assumptions for Macs is actually written in CryptoVerif, because it will give you an idea of how you can write other primitives as well, even though this one is already in the library. So we're going to, as usual, have three functions. There's a MK key generation function called mkgen, a MAC function, and a verify function. We are going to assume that the verify function gives us this functional correctness guarantee, which is that verify of applied to something which actually is a MAC will return true. And then we want to say that the adversary who has oracle access to MAC and verify for a particular well properly generated key has a negligible probability of forging the MAC, right? You've seen various ways in which this can be formalized and in paper proofs, but let's see how it's actually done in Cryptoverif. So the intuition for how it's coded in Cryptoverif, and there are actually paper proofs to show that this encoding is exactly the same as the way you think of UFCMA, is that first of all, the adversary should not be able to forge a correct MAC. Okay, so what this means is that if a key was generated properly using mkgen, and then it was used only in generating in the MAC and verify function, it wasn't used anywhere else in the protocol, then verify can succeed only if the MAC that you are trying to verify was in fact in the list or array of values that was actually macked by the MAC oracle, right? So you want to say that the verify oracle will succeed only if the values provided to it are exactly the same as the values that were used in the MAC oracle in some previous session, some independent session. So in Cryptoverif, there is a way in which you can query from one process, you can query the values that were assigned in a different process. Now this is kind of query is not something that you will ever use in a protocol model, but this is something that appears while you're doing the proof. So for example, at the bottom there is a expression called find, where what you can say is when you want to verify a MAC, instead of actually computing the actually doing verify, you can do a instead of you can replace the verification by something like that, which is what it's going to say is go find me a session of the macking oracle where the value I'm trying to mac was exactly the one that was macked there, and if you find such a session, then you run the verification of the MAC, and then you tell me whether that succeeded or not. Okay, so you can use that assumption, which is that verify will only succeed if the value you're trying to verify was macked in some previous session, to transform the verification function into something which has a stronger guarantee. Okay. So in particular, this is the model of UFCMA MACs in Cryptoverif. It says that suppose you have a game, and in that game you have n double prime copies of a MAC key seed R. So there are R instances, or there are n double prime instances where you have a macking key. For each of those macking keys, there are n instances of MAC and n prime instances of verify. Okay, and there is no other place in the entire game where this macking key is used. The MAC key is used only for macking and verify, and there are n double prime such keys which are used n times for MAC each and n prime times for verify. Then you can replace this pair of functions, or every instance where this function is being called, by this pair of functions, where you keep the same number of keys, you replace every MAC by a MAC prime. Actually, I didn't write it as a MAC prime, but it's really the same. You don't do much to the MAC function, you keep it as it is. But every time you see a verify, you replace it by something like this, where the verify, what it's now going to do is going to look up the table of things that were macked before. Okay? And it's only going to succeed if the value I'm trying to verify was macked before. So this is the definition of, this is the game transformation defined as an equivalence relation in Cryptoverif. Okay, so what the Cryptoverif prover is going to do is going to take a rule like the one I wrote there, which is that you can take a MAC keygen MAC and verify triple and replace it with a keygen prime MAC prime and a verify prime triple like the one at the bottom, and it's going to try and apply it any number of times within polynomial context, perhaps replacing several instances of MAC and verify each time. Okay, and it'll keep trying to apply it until it cannot apply it anymore. So this is something that it will do automatically, but you can also guide it by saying, okay, I want you to apply this assumption on those two instances, but not on those two instances, and so on. You can also try to formalize other assumptions like SUFCMA, et cetera, in a very similar style. So we are also using encryption, right? So for encryption, we have the following assumptions. The first is obviously functional correctness of decryption. And then this is your INCPA assumption written in Cryptoverif. What it's saying is that every time suppose in your initial game, you have n prime copies of some key seeds. And for each of those, you have n copies of an encryption, n instances of an encryption applied with that key. And there is no decryption. Yeah? There's no, you're not allowed to decrypt with that key at all. Then you can replace all of those instances with instances of this form, where you're not actually encrypting the message, you're encrypting zeros of the same length. Okay, it's a very syntactic rule that we are describing here on how you can apply the INCPA game transformation on a process which is using encryption, for which you want to make this assumption. This again is a Cryptoverif rule which corresponds to a game transformation that Cryptoverif knows how to apply any number of times. Okay, we can also do public key encryption, INCC encryption, blah, blah, blah. So what is Cryptoverif going to do when you give it a bunch of these assumptions and the protocol model and say, please prove to me secrecy of K prime? The first thing it's going to do is a bunch of syntactic transformations to simplify your protocol. The first kind of syntactic transformation it does is expansion of assignments. So if you have something like let mk equals mkgen, then it's going to say, oh, okay, this is a key generation function. I can eliminate this, and I can just inline the mkgen everywhere. So this is just a simple inlining thing that you can do in your entire game and simplify some expressions that you see. So this is something kind of very trivial in a certain way, except that in Cryptoverif, since we are able to also from one process refer to variables in a different process, you have to be careful when you're inlining all those variables and eliminating them that your game is still well formed. You're still able to read from one process the variables that you need from the other process. You're not allowed to inline everything. The second kind of transformation that you do is a single assignment renaming, which means that if you have two variables for the same name, then you want to give them different names and distinguish all their use cases. Okay? So this is something that sometimes happens in source protocols where you accidentally use the same variable name for two different things, but that's not so common. What happens is that as you are applying your game transformation, your transformations might introduce to you in your game two different variables which have the same name. And now you have to basically distinguish them by giving them different names. So this is called single assignment renaming in Cryptoverif. And that might actually expand your protocol quite a bit, because here you have two variables, K prime in the if case and K prime in the else case. And you want to basically distinguish those two cases. So what you might end up doing is saying, okay, I'm going to call the first one K1 prime and the second one K2 prime. But that means that anywhere else in the whole process where you are referring to K, you have to decide which one you're referring to. And you might have to make a case analysis everywhere saying, oh, it's either K1 prime or K2 prime, and expand out your process. Again, this is a very syntactic thing that you do. And you can prove that this transformation is sound in the sense that this does not change the probabilistic execution of the source process. And this is something that automatically is implemented by Cryptoverif, right? I would suggest that these are the boring transformations, which are not the crypto transformations, but are likely to be the transformations where you might introduce bugs in our proofs, because they are kind of really syntactic. There are too many variables around, and we are doing these implicitly and almost when we are doing our hand proofs. But this is kind of the thing that you really want the tool to just take care of and not actually look at much. The last kind of syntactic transformation that's interesting is that if you're generating a fresh nonce like X, and then if you do a conditional after that, you go to if C, then you do one condition, an else condition, then you might be able to move this random nonce generation into the two branches. And this kind of helps in many cases, because if the condition is false, then you might be able to get rid of the entire branch in one direction. There are many other such simplifications. If you do if then else, if you do various things. There are many syntactic transformations you can do, many simplifications you can do based on what the structure of the game is and so on. And Cryptoverif does a sequence of them. Okay? And the whole point is, after doing all this syntactic transformations, it will be ready to apply the real game that you care about, which is your cryptographic game. So let's now, okay. So how does it prove secrecy? Well, doesn't matter. It's the basic idea is that if you have a secret that you want to prove is kept secret by the game, then what you have to show is that this particular secret either has been eliminated from the game altogether by just rewriting, the secret no longer exists, or even if it exists, then there is no, it does not affect the control flow or the outputs on any channel in any way. So in fact, there is no information flow, so to speak, between this secret and anything that goes out on the network or anything that affects the control flow of any process. So this is what Cryptoverif does. It tries to execute each transformation that you have provided it in any sequence. First, it tries to do all the syntactic transformations. Then it tries to apply crypto primitives. If it cannot apply a crypto primitive, it goes back and tries more syntactic transformations, and then it tries to apply the crypto game again over and over until it finally gets to a game which is trivially true. Now, since there are many, many possible sequences that it could try, you might have to help it. Okay, so sometimes it is not able to find the proof, and you have to guide it through the right sequence of games in order to get to the proof. So let's do a example proof of the Mac, of the encrypt and Mac game that we had, which is this one, which is our initial protocol, and we want to prove that K double prime, which B has received here, is secret. So the first thing that Cryptoverif will do is it will take the MK macking key up there, which is on top, and it will inline the definition of the macking key everywhere, so that we get the Mac, and the verify is the only place where the macking key is being used. And now Cryptoverif identifies this and says, this matches the UFCMA pattern, where there is a key seed that is being used up there, which is the R prime. There is instances of Mac and verify. There is n instances of Mac and n instances of verify over here. And I can take all of them and I can replace them with using the UFCMA game transformation. So the Mac here becomes Mac prime, which is really the same as Mac. There's no difference. And the verify becomes this thing, which is doing actually a table lookup. And what it's doing here is that when we are doing the verify, we look up and say, is there an instance of the other process where the value for which I'm trying to verify the Mac, which is E prime, was in fact the exact same as the value for which was macked on the other side, which is E. So this assumption down there, which is E prime equals EJ, is the crucial one. That's where I'm looking at the table. I'm looking at the table of E's that have been macked on the other side, and I'm saying the value that I'm verifying here has to be one of the E's that was assigned in some session of QA. And this is valuable because if the E prime that I'm trying to verify is one of the E's on the other side, then I know what the shape of E is. E has to be of the shape enc of K to B of K prime of K and R double prime. So I know what the shape is, and I can now simplify further. So it knows that the decryption down there is being applied to an encryption. So it uses that to simplify the decryption, and it obtains that the K double prime down there is actually equal to the K prime that was sent from the other side. Okay? So by applying the UFCMA game, we have managed to get rid of decryption, and this was our main goal here. Because once we have gotten rid of decryption, now we can apply the int CPA game. Until then, we could not apply the int CPA game. So we've gotten rid of decryption there. Then we can inline the key for the encryption, which is kgen of R, and then we can apply the int CPA game to get zeros instead of the message we are trying to send. Okay. And now we get the fact that the thing that we are encrypting is actually zeros, and we look at this last. This is pretty much our last game. We look at the game and we say that the only instances of K double prime and K prime in this whole protocol are there. A is generating K prime up there, and B is magically getting K prime down there. It's got it from the verification. And since K and K prime are not affecting the control flow in any way, and they're not sent on any output channel, this one is trivially preserving the secrecy of K prime and the one session secrecy of K double prime. Now it's worth seeing here why K prime is secret, but in fact K double prime is one session secret. K prime is secret because every instance of QA generates a fresh K prime, and you're sending it out. Every time you send out K prime, you're sending out a new K prime. So different sessions of A do not generate the same key, and they're all independent random numbers. And so K prime is actually secret. Whereas K double prime is not multi-session secret because in fact the attacker could replay in this protocol the same K prime to multiple instances of B, and each of them will end up with the same K double prime. So B doesn't get full secrecy for K double prime, it only gets one session secrecy for K double prime. Okay, so let me just show you how this looks like in code. All right. So this is CryptoVerif. This is more or less similar to how ProVerif looks, but it has some more stuff in it. So what we do is for the shared key encryption, which is for symmetric keys, we basically say that we have these functions and these types. There's a key C, there's a key, and there is an enc-dec function and a keygen function. The keygen function is, let me put it here. So importantly, there are these three functions, keygen, enc, and dec, which together satisfy INCPA, which is in the CryptoVerif library. We define some notion of zeros of a particular length, and which is called ZK. Then we define for UFCMA, there is a triple of functions again, which is, where is it? Down there, hang on. We say that there's a triple of functions, mkgen, mac, and verify, that together satisfy the UFCMA assumption. Then we are trying to prove that the K double prime is secret and K prime is secret. Those are our goals. The protocol itself is the one that we saw earlier. QA is written like this. It's some number of copies up to n of this process, which is Mac, encrypt and Mac. QB is that one. And the initial process is the one that we saw. We are generating the key, generating the MAC key, and passing them to QA and QB. Okay? So this is the process. You want to prove the secrecy there. So if you run CryptoVerif on this, let's look at the result. Okay, first, let's just look at what it says. What are the main results it provides us here. And so the result it says, the top one, it says I could prove the secrecy, which is multi-session secrecy, of K prime up to probability, blah, 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 blah. So it gives us the time for game 6. No, actually it's rolled around. Yeah. So it's in terms of the amount of time that the attacker can spend in its computations, in terms of the number of copies of each process, which is little n, the length of the key, the maximum length of some other parameter somewhere, and so on. So there are a whole bunch of parameters that come in. Typically, since we use a little n to parameterize all the copies everywhere, we could have used n1, n2, n3. It would have given me different variables there. I just used n everywhere. So it gives me a big formula in terms of that little n and the amount of time the adversary can spend attacking various things, to say as long as that particular number is small, it's going to be the attacker cannot break the secrecy of K prime, and under certain assumptions it has actually proved that formula over there is negligible. Similarly, that has properties for this, for K prime, K double prime, and then it actually says that blah, blah, blah. It finally calculates that it could not prove the secrecy. It could not prove the secrecy of K double prime. It could only prove the one session secrecy of K double prime. And this is the case I was telling you about, that the attacker could replay K prime twice to two different instances of QB, so you don't get multi-session secrecy of K double prime. Right, so that is a probability which should appear hang on. So there's p-enc. You see that p-enc? That's the advantage of the attacker breaking the in-CPA assumption, and we instantiated it in the in-CPA assumption in the script. And pmac is the probability function that we gave to the UFCMA assumption. So they appear in the formula too. Yeah. Yeah, and there are other ways of printing out this formula which might make better sense to some of you. But yeah, so this is the kind of analysis it has done. And it's also worth looking at what it actually does. So this is saying, okay, this is what Cryptoverif is doing. It's trying to apply all of these simplifications, and then it says, okay, I'm now going to start the proof. This is my initial game, game 1, which looks like this. Then it is going to say game 2 is, this is what the transformations I did. Now I got game 2. Then I applied the UFCMA assumption right here, and I used some other expansions, and I got game 3. Then I applied some other simplifications based on what the meaning of find is, and I got game 4 and so on. So you can keep going. Let's see how many games it has. Well, 8 games. It's not so bad. Okay. For TLS 1.3, it gets into hundreds of games. So, but this is 9 games, and the final game is, let's see whether it's actually trivially correct. Yeah, let's look at this one. In the last game, we have let k double prime equals k prime here, and there should be no instance of k prime or k double prime anywhere here. K prime is a key which is generated here, and there should be no instances of k prime or k double prime here. So just by looking at that k prime and this line and seeing that there's no other instance of these secrets, and the fact that these values are not affecting the control flow or the outputs in any way, it's able to establish that the attacker has 0 advantage in breaking this game, and then it's able to go back through the series of transformations it did and give us a formula for the advantage the attacker had of breaking the first game. Okay? So this is the kind of analysis that Cryptoverif can do. In this particular case, it did it completely automatically. In some cases, it can do it automatically, but it may not find the kind of the most efficient sequence of transformations. You might know of a better way for it to have done the proof, in which case you can guide it. So there's a way of guiding the prover through a sequence of transformations.
Can you prove that the one-time bad is CPA?
So I don't know. Normally in Cryptoverif, you don't prove that things are in CPA. I mean, so it's better for taking constructions up with which satisfy a certain assumption and proving protocols on top of it. There are some constructions for which there have been proofs in Cryptoverif, but typically you would take something like a one-time pad, assume that it's in CPA, and then build on top of it. In EasyCrypt, on the other hand, I think you can actually do proofs like that as well, all the way down to pretty much primitives. But on this particular question, I don't know the answer. So what you can do is, right, so that you can try to prove. So you can try to show, for example, that if you have in CPA and UFCMA, then you get you can do the proof of authenticated encryption using in CTXT, in PTXT, and so on. And you can do that proof for encrypt and MAC. For MAC and encrypt, you need completely different assumptions to succeed. Oh, that is wrong, yes. I'm not sure how insightful it is, but it's very syntactic. So it'll basically say that if you're trying to apply this assumption, you cannot apply this assumption right now because there is an instance of decryption that you have had to give to the adversary. The adversary actually has this decryption oracle that it can apply for certain keys, and you've not been able to eliminate that decryption, so your in-CPA game is useless to you. So you're not able to apply that the in-CPA game at all, so you will never make progress in the proof towards in-CCA. So it will say, I tried to apply this game, but I failed. I did lots of simplifications, but I still cannot apply this game. And then from that, you can try to kind of tease out where it actually broke, or from what it tried. But it's not always obvious. All right, so let's take a break, and when we come back.